Okay, so as we've just discussed, conformal field theories are extremely useful for understanding RG flows. They describe the start point and the end point of the trajectory of an RG flow in the space of all field theories. And a single trajectory corresponds to a single quantum field theory, and points along the trajectory correspond to quantum field theories defined at a specific scale. What I want to start doing now is I want to describe the relevance of conformal field theory to describe phase transitions. So what is a phase transition? Well, here we're in the realm of statistical mechanics, and we've got a collection of particles, and they can really find themselves in two different phases. So a good example, for example, would be water. Well, if you freeze water, you know it forms this nice regular array of atoms, some solid. That's at low temperatures. But if you go to very high temperatures, well, you'll find water. And it's a completely different phase of the water molecules. And there's many examples, a state where a bunch of spins are pointing the same way, so that your sample is magnetized at low energies versus at high energies where there's no magnetism. The spins point all over the place. And what I want to start off by explaining is that, phase transitions can be understood as a competition between entropy versus energy. And this is a correct statement for any equilibrium phase transition. There are examples, for example, zero temperature quantum transitions and non-equilibrium transitions, where you have to be more careful about what entropy and energy actually mean. But for us, we'll focus on equilibrium phase transitions. And then it's perfectly good to think that what's going on is we've got a competition between entropy and energy. Okay, so to make the point, I'm going to introduce an incredibly simple toy model. Maybe we don't even need such a simple toy model, but let me just introduce it. So let's say toy model. Good, so we'll put it here. And let me underline it. And let's go back to black. So this model, I'm going to imagine a system, a very simple system. It's got two energy levels. So we can find our particles in the state with energy E1, or we could find our particles in the state with energy E0. And let's imagine that the state E1, it's not just a single state here, there's a degeneracy. Let's imagine that, in fact, there are n different states and that n is very much greater than 1. And later on, I will explain why. And that's a pretty reasonable assumption. It models a lot of interesting physics. Although, of course, this model is too simple to actually describe anything in nature, but it captures, well, the effect that we want to discuss. And then this lower energy, there's only a single state, so there's no degeneracy associated with that. Okay, good. And of course, I mean, I've drawn it, but let me just make that absolutely explicit. The energy E0 is less than the energy E1. Now, since we're in statistical mechanics, well, we like now to talk about the probability with which a given state can be occupied. And we know that, well, Boltzmann taught us that the probability with which we occupy state I is given by the Boltzmann weight, so E. Okay, so it's given by E. Oh, come on. It's given by E to the minus beta EI. Good. And in fact, the probability is just proportional to that. We have to normalize it. The probabilities must sum to 1. We do that dividing by Z, the partition function. So Z, as usual, is just given by the sum over I, e to the minus beta EI. And let me remind you that beta is the inverse temperature. Okay, so these are really the results that I want to use from statistical mechanics. Just the Boltzmann weight, the Boltzmann probability for occupying a state of energy EI. And there's two different limits that I want to study. So in the first limit, I want to study low temperature. Okay, so low temperatures. And by low temperature, what do I mean? Well, I'm actually going to imagine that I'm taking T to 0. So equivalently, I can think that I'm taking the limit that beta goes to infinity. So let's work out now the probability that we're in the state E naught. So the probability that we're in the state E naught is just given by e to the minus beta E naught over z. And what's the probability that we're in the state E1? Well, it's e to the minus beta E1 over z, but actually I should multiply by n, because if I'm in any of the n degenerate states, I have an energy E1. And what are we doing? So here's the real important thing that I want you to pay attention to. We're taking beta going to infinity. And because we're taking this limit that beta goes to infinity, well, we know that both of these exponentials are going to get very small, but E naught is less than E1, which means that the probability of E1 is getting smaller exponentially faster than the probability for E naught. So in this limit, what we find is the probability of being in the ground state is equal to 1, and the probability of being in the excited state is equal to 0. And let me make a very clear statement, and make sure you understand this. The n doesn't matter. Who cares what the value of n is? It can be any fixed number that's arbitrarily large, even if it's much bigger than 1, as we said. Who cares? Because the probability of being in E1 is getting exponentially smaller than the probability of being in the ground state. And that's because in this low temperature limit, only energies matter. So what I mean by that is, if you are the lowest energy state, then that's the state the system will find itself in as you take the temperature to 0. So in this low temperature T tends to naught phase, only energies matter. Okay, good. Now let's look at high temperatures. So we'll look at high temperatures. So in high temperatures, what's going on? Well, we're taking T to infinity, and that means that beta is going to 0. Now, if beta is going to 0, what happens to these exponentials? Well, let's take a look at them, okay? Look at probability of being in the ground state. Because beta is going to 0, that e to the minus beta E naught just goes to 1, and we get 1 over z. And look at the probability of being in the first excited state. In the first excited state, we've got an n, and then again, beta is going to 0. So this exponential is just 1. So we've got n over z. So now in this phase, the energies don't matter. Who cares what the energy of the state is? In these final probabilities that we've written down for PE naught and PE1, you can see the energy doesn't even appear there in the temperature goes to infinity limit. So energies don't matter. Who cares what the energy of your state is? Only n matters. And if n is much, much bigger than 1, only n matters. So let me try to move this over. Good. Only n matters. Okay. And that's what happens in the high temperature limit, that only the n matters. So if n is much bigger than 1, we'll find ourselves in the state E1, not in the state E0. So this is the message that I want you to take with you. At very low temperatures, the only thing that matters is energies, and you don't care about degeneracies for states. At very high temperatures, you don't care about energies. The only thing that you care about is the degeneracies of states. So that's the difference between the low temperature and the high temperature limits of the system. Okay, now let's relate that to phase transitions.